Hello everyone, my name is Rani. I am studying at Institute of Aeronautical Engineering, BTech second year CSC, C section. My roll number is 22955A0515. Today I am going to give presentation on generating predicate logic expressions from natural language. So let's see. My contents are my topic contains are introduction, predicate logic, quantifiers, useful of predicate logic from natural language, and examples. Introduction. Discrete mathematics is the study of mathematical structures that are countable or otherwise distinct and separable. Means discrete mathematical structure is nothing but countable. Means we can count it and it is separable, or else it is separable and distinct. Examples of structures that are discrete are combinations of graphs and logical statements. So, discrete structures can be finite or infinite. So, this discrete mathematical structure is nothing but countable thing and distinct and separable. These are the combinations of graphs and logical statements, and discrete structures can be finite or infinite. Predicate logic. A predicate is an expression of one or more variables determined on some specific domain. A predicate with variables can be made a preposition by either authorizing a value to the variable or by quantifying the variable. The following are some examples of predicates. Consider u of x comma y. Denote x is equals to y. Consider x of a comma b comma c. Denote a plus b plus c equals to 0. Consider m of x comma y. Denote x is married to y. So these are the examples of predicate logics, and so these predicate logics are determined, one or more variables determined on some specific domain. So the expression of one or more variables determined on a specific domain. So these can be made by authorizing a value to variable or by quantifying the variables, and as we see in the examples. Quantifiers. So let's see what is quantifiers. The variable of predicates is quantified by quantifiers. There are two types of quantifiers in predicate logic. They are extensional quantifier and universal quantifiers. So extensional quantifier, if p of x is a preposition over the universe u, then it is denoted as e of x, p of x, and this can be reached as there exists at least one value in the universe of variable x such that p of x is true. So here this capital E, delta E is there is nothing but there exists at least one value in the universe of variable x such that p of x is true. The quantifier is called the extensional quantifier. That symbol is called as extensional E symbol is called as extensional quantifier. There are several ways to write a proposition with an extensional quantifier. Example, for any of x belongs to a, p of x, or p of x for any x belongs to a, or for any x comma p of x, or p of x is true for all x belongs to a. Phrases used in extensional quantifiers are there exist, there is at least, there is an. Means only saying for limited things, not for all. It's like there exist, there is at least one, there is an, in such a way. There exists one such thing that x belongs to a, p of x, or such that p of x or e of x, p of x, or p of x is true for some x belongs to a. So universal quantifier. Let's see what is universal quantifier. If p of x is a preposition over the universe u, then it is denoted as for all or for any x belongs x comma f p of x, and read as for every x belongs to u, p of x is true. The quantifier a is called the universal quantifier. There are several ways to write a preposition with a universal quantifier. Phrases used in universal quantifiers are all, or for every, for any, for all. So, extensional quantifier is a preposition of over the universe u. Then it is denoted as for every of p of x and read as for every x belongs to u, p of x is true. And there are several ways to write a preposition with universal quantifiers, and phrases used in logical expressions. The phrases used are all, for every, for any, for all, in such a way. These are used in universal quantifiers and useful of predicate logic for natural language semantics. So let's see what is the use of predicate logic. While in prepositional logic we can only talk about sentences as a whole, predicate logic allows us to decompose simple sentence into smaller parts, predicates and individuals. For example, John is tall, or T of J. Predicate logic provides a tool to handle the expressions of generalization. Quantificational expressions are every cat is sleeping. Some girls likes David. No one is happy. Predicate logic allow us to talk about variables pronouns. Means these allow us to talk like a talk about the variables like John is tall. Right. Every cat is sleeping. Some girls like David. No one is happy. In such way, these are the examples. The value for the pronoun is some individual in the domain of universe that is contextually determined. For example, it is sleeping. She likes David. He is happy. Sentences with quantification expressions can be divided into two interpretive components. Every cat is sleeping, or we can write it as every cat it is sleeping. So we can convert this into our logical expression as, let's take this example only. Every cat is sleeping. In our expression we write every cat it is sleeping. Here, for all x, x is a cat, x is sleeping. Here we are taking x as a cat. Okay, for every cat it is sleeping, right? Cat we take as a x, and for all of x, x is a cat. Every cat in the sense for all x, and here x is a cat, and it is sleeping. That is, x is sleeping. Here x is x in the sense cat. Cat is sleeping. We are the same meaning will be there. Every cat is sleeping, or for all x, x is a cat, x is sleeping. In such a way. True if it is sleeping is true for all possible values for it in the domain. True if it is sleeping. If it is sleeping, it is true for all possible values of it. For all, we have written for all x is a cat, x is sleeping, right? So possible values for it, for all possible values of for it in the domain. A simple sentence containing a variable pronoun, a placeholder. It can be evaluated as a true or false with respect to some individual contextual taken as a value for the pronoun. The quantificational expression. Let's see what is quantificational expression. It instructs us to limit the domain of individuals being considered to relevant set. A set of cats, for example, is a set of cats, a set of foxes. In the sense, it limits the domain. It instructs us to limit the domain of individuals being considered to relevant set. Examples are a set of cats, and tell us how many different values of pronoun we have to consider from that domain to establish a truth for the sentence. So it tells us how many different values of pronouns we can consider from that domain to establish a truth for that sentence. Examples. See, um, let's see the examples for it. Suppose we have two predicate variables. They are x and y, where the domain for x is f, in the sense false, and y has the domain s, in the sense nails. where p of x comma y is foxes are better than snails. We have took of two variables, they are x and y, and here x is fox and domain is snail. Okay, we where p of x comma y is foxes are faster than snails. We have to say that in the logical expression. So now we wish to write the following statement using logical symbolism and quantifiers. By using logical symbolism and quantifiers, we have to write that statement. All foxes run faster than all snails. Here, all foxes. For example, question here we have took this, that all foxes run faster than all snails. Here, this all in the sense it is a universal quantifier. If there is a like there is any in the sense, then it is exponential quantifier, right? Here, all foxes run faster than all snails. So we can write this statement in a logical symbolism as for any of x. Here x we have took x is equals to uh, x is fox and y is snails, right? So by using the x and y variables, we have to create the sentence which should be same as the question, that is all foxes run faster than all snails. So here for any of x, for x, for any snail y, such that x is faster than y, in the sense x is in the sense foxes, fox is faster than snails here. So logical symbolism are for any of x belongs to f, that is fox, for every y belongs to s, that is snail, p of x comma y. We are writing the total syntax p of x comma y. If we consider all of that, for every x belongs to f, for every y belongs to s, p of x comma y. We have written the sentence in the logical symbolism. Let's see another one. Question, that is every fox is faster than some snail. Every is a universal quantifier, is faster than some snails. Some in the sense it is limited, that is it is extensional quantifier, it is extensional quantifier, right? So we should convert this statement into logical symbolism. So let's see. For any of x, as I said before, for any is a universal quantifier. For any of x, here we took x as a fox and s as a snail, right? For any of for any for x, there is a small snail y. There is a a is a extensional quantifier. So there is a snail y such that x is faster than y. Fox is faster than y. See the difference here. Every fox is faster than some snail. Here we are using universal quantifier, extensional quantifier, but here see all foxes run faster than all snails. Here we are using only universal quantifier. Okay, that is the difference. Okay, for any for x there is a snail y such that x is faster than y. And if we convert this into logical symbolism, it is for every of x belongs to f, extensional y belongs to s, p of x comma y. For every x belongs to f, extensional quantifier y belongs to s, p of x comma y. So this is a example for that. So we have used here extension aligned universal quantifier, but here we used only universal quantifier. By using, we have seen a keywords for that, for any, for every, for all, and all are extensional quantifier phrases, sorry, universal quantifier phrases. And extensional quantifier phrases are there exist, there is, and there that's it. Okay, and let's see another one. There is a fox that is faster than all snails. Here, we first, there is a fox. There is a. In the sense, it is existential. That is faster than all snails. All, in the sense, it is a universal. Let's take fox as x and snails as y. There x, there is x that is such that y for faster than all snails there is a fox means there is it is a extensional, right? There exists a fox, we can write it as there exists a fox. That is converted into such that faster than all snails in the sense it is a universal, means we can write it as for any snail y, x is faster than y, x is in the sense fox is faster than y, right? It will become the same meaning. So in the logical symbolism it comes like extensional x belongs to f, for any y belongs to s, p of x comma y. Here it will come like extensional x belongs to f comma, for all y belongs to s, p of x comma y. So in such a way convert it into we can convert into expressions, logical statements into a logical symbolisms. So these are the examples of it. I have used snails and foxes. You can use many others also. So here there is a here we see an example. Every cat is sleeping. We can take like we can take a normal language and convert it into uh, predicate logic expressions. We can do that, and these are the examples of predicate logic. And thank you.